You need to watch this if you panic every time the ground shakes. It's a primal, terrifying feeling. The solid earth beneath our feet suddenly turning violent and unpredictable. And if you're driving, that fear can be magnified 100 times over, especially if you find yourself on a bridge suspended high above the ground. But what if I told you that many of those bridges are designed with that exact moment in mind? I don't think people fully appreciate just how intelligent modern bridges really are. They aren't just static, rigid structures of concrete and steel. They are dynamic, responsive systems, engineered to dance with the very forces that seek to destroy them. To understand this engineering marvel, we first need to understand the enemy, the earthquake itself. When an earthquake strikes, it sends seismic waves rippling through the Earth's crust. These waves make the ground move in complex ways, up and down, side to side, and in rolling motions. For engineers, the key metrics aren't just the magnitude you hear about on the news, but the ground's acceleration and the frequency of the shaking. A fast, jerky shake affects a structure differently than a slow, rolling one. The goal isn't to build a bridge that can resist these immense forces head-on. That would be like trying to stop a tidal wave with a brick wall. The real secret is to not fight the earthquake at all. The principle at play is a combination of inertia and ductility. Inertia is an object's resistance to a change in its state of motion. When the ground suddenly lurches sideways, the massive bridge deck to stay put. This creates colossal stress where the deck connects to the piers. If the structure is too rigid or brittle, that stress has nowhere to go, and it will fracture, just like a piece of chalk snapping under pressure. But if the structure is ductile, meaning it can bend and deform without breaking, it can safely accommodate that movement. The strategy is to make the bridge flexible in all the right places. And the first line of defense is a concept called base isolation. Base isolation is a revolutionary idea that essentially decouples the bridge's superstructure, the deck you drive on, from the substructure, the piers rooted in the ground. This is achieved using special bearings. Think of them as seismic shock absorbers. Instead of being rigidly fused together, the bridge deck rests on these bearings, which allow it to slide, or isolate, from the violent ground motion. While the piers are shaken forcefully by the earthquake, the bearings absorb and dampen that energy, allowing the deck above to move much more gently, or even remain relatively still. This dramatically reduces the inertial forces transferred into the main structure. These aren't just simple blocks of rubber. There are several highly advanced types. Lead rubber bearings, for example, consist of alternating layers of steel and rubber, with a solid lead core in the middle. The rubber provides flexibility, allowing the bridge to slide, while the lead core deforms and heats up, dissipating the quake's energy as heat. Another ingenious design is the friction pendulum bearing. This works like an upside-down pendulum. The bridge is supported on a slider that rests on a concave, dish-like surface. When the ground moves, the slider glides along the curved surface, increasing the natural period of vibration and using gravity to gently recenter the bridge once the shaking stops. But allowing the bridge deck to move creates another challenge. What happens at the ends of the bridge, or between its different sections? This is where expansion joints come in. You've driven over them thousands of times. They're the metal-toothed gaps in the roadway. While they are designed to handle normal thermal expansion and contraction in seismically active regions, they are engineered to accommodate massive movements, sometimes several feet in any direction. These joints allow sections of the bridge to move independently without hammering into each other. They are often paired with seat extenders, essentially wider ledges, to ensure that even if the deck slides, it has plenty of room and won't fall off its supports. While base isolation and flexible joints manage the big movements, engineers also employ devices to actively counteract the shaking. These are known as energy dissipation devices. One of the most impressive is the tuned mass damper. This is a massive weight, sometimes hundreds of tons, mounted on springs or hydraulic cylinders, often hidden inside the bridge's pylons or deck. It's tuned to the bridge's natural frequency. When the bridge starts to sway, the damper swings out of phase like a counterweight, pushing back against the motion and canceling out the most violent vibrations. Other devices, called viscous dampers, work just like the shock absorbers in your car, but on a colossal scale. These hydraulic cylinders are placed strategically throughout the structure. As the bridge moves, they force a thick fluid through a small opening, converting the kinetic energy of the earthquake into heat, which safely dissipates. They act like a seatbelt for the whole span, slowing and smoothing out the jolts. The materials themselves are also part of the solution. Modern seismic design focuses on what's called ductile detailing. Concrete, while strong in compression, is brittle in tension. To counteract this, it's reinforced with steel bars, or rebar. In seismic zones, this rebar is configured in special ways. For instance, columns are often wrapped in a dense cage of spiral rebar or a steel jacket. This confinement prevents the concrete from bursting outward under stress, allowing the column to bend and flex without failing. It's about ensuring that if failure does occur, it happens in a slow, controlled, ductile manner, not a sudden, catastrophic collapse. But what if a component does fail? That's where redundancy comes in. Engineers design bridges with multiple load paths. This means that the forces holding the bridge up can travel through the structure in several different ways. If one column, cable, or girder is damaged, its load is automatically redistributed to the surrounding elements. This principle of redundancy is a cornerstone of modern engineering, preventing a localized failure from cascading into a progressive collapse of the entire structure. It ensures that no single point of failure can bring the whole bridge down. A bridge's resilience doesn't end with its construction. It requires a lifetime of care. Routine inspections are critical for identifying wear and tear, corrosion, or damage that could compromise seismic performance. But today, we're moving into an era of smart bridges. Many are now fitted with a network of sensors, accelerometers, strain gauges, and GPS monitors that act as a permanent nervous system. They continuously monitor the bridge's health, and during an earthquake, they provide invaluable real-time data on how the structure is performing. After a major event, this data allows engineers to quickly assess the bridge's integrity and determine if it's safe to reopen. Of course, not every bridge was built to these modern standards. Thousands of older bridges are still in service. That's why seismic retrofitting is one of the most important ongoing infrastructure projects worldwide. This involves strengthening older structures to meet current codes. Engineers might wrap columns in steel or fiber-reinforced polymer jackets to increase their ductility, add new isolation bearings, or install external dampers and restrainer cables. It's a massive, complex, and expensive undertaking, but it's essential for protecting our vital transportation arteries. The proof of these designs is in their performance. In major earthquakes in Japan, Chile, and California, modern, seismically designed bridges have performed exceptionally well, often reopening to emergency traffic within hours. At the same time, the tragic failures of older, non-ductile bridges in past quakes have provided invaluable, if harsh, lessons. Every failure is meticulously studied, leading to stronger building codes and more innovative designs. It's a continuous cycle of learning and improvement, driven by the goal of ensuring public safety. So what should you do if you find yourself on a bridge during an earthquake? The advice from experts is clear. Don't panic and don't stop. Your car's own suspension provides some isolation. Grip the steering wheel firmly, slow down gradually, and keep moving toward the end of the bridge as soon as the most violent shaking subsides. Stopping on the span can create a hazard for others and for emergency responders. After the event, always follow the guidance of officials and respect any bridge closures. So the next time you drive across a major bridge, take a moment to look at its design. See the massive piers, the thick cables, the gaps in the roadway. They are not signs of weakness, but symbols of incredible strength and intelligence. They are a testament to generations of engineers who have learned to turn chaos into controlled motion and transform a potentially catastrophic disaster into a survivable and ultimately awe-inspiring feat of human ingenuity.